So now we're going to start talking about section 3.1, polynomials. Now I know we've already done a fair amount of stuff with polynomials, but this is going to be treating them more formally. So suggested exercises are 5, 7, 15, 17, and 21. I'd like for you to review definitions 3.1 and 3.2 in the book. And we're going to talk about something called multiplicity. I want you to look at the sign diagram on page 242. I think I have mentioned sign diagrams before, or sign charts. So this is going to be what I had mentioned before. And finally, work through examples 1 through 3. Okay, so a polynomial takes the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub 0. Okay, so this is a polynomial, and I'm going to tell you some things about it, some characteristics of it. So where n is a natural number, called the degree, and you might see a little bit of fuss if we have, we've got a sub n is non-zero. A little bit of fuss, you might say like, well, isn't f of x equals a constant a degenerate polynomial, and then it would have n equals 0, and sure, fine, whatever. But for the most part, n is a natural number called the degree of the polynomial. A sub n x to the n is called the leading term. And a sub n, well, I guess I don't need a conjunction yet. A sub n is called the leading coefficient. You've already heard me say a lot of these words. Leading coefficient. Man. There we go. Nailed it. And finally, a sub 0 is called the constant term. Okay. So you probably heard me say things like the leading coefficient, blah, blah, blah. And again, I'm assuming that many of you have seen this before, but now we're treating it a little bit more formally. So let's do a quick example of a polynomial. What is the volume of a rectangular box with no top, made by taking an 11-inch by 17-inch sheet of cardboard, cutting squares out of the corners and folding up the sides. Now, if I was really asking this question of you, I would describe it a little bit better. I'm describing this rather quickly because I'm going to give you a diagram. So if I was actually asking you for an answer to this question, I would give you a little bit more prompting, or, well, now that you've seen it. But let's start with a diagram. So I would try to be a little bit more careful about what I mean by cutting squares out of the corners. So what I mean is I've got this 11 by 17 sheet of cardboard. So this is 17 inches, this is 11 inches, and my little inches symbol's got a little funky. This little quote means inches. And what I'm going to do is I'm going to cut the corners out, and then I'm going to fold along the dotted lines. And when I fold these up, then I'll get a box like this. So I'll have something like this. And this is a box with no top. So here's the back end of the box. Whatever. Maybe it'd be better if I sort of shaded these things so you can see the vertical part. Maybe that helps a little better. Okay, so what's the volume of this box? Well, it's going to be this dimension times this dimension times this dimension, right? So let's call this the length, the width, and the height. So the volume is going to be length times width times height. And what is that? Well, since I'm cutting out an x by x, see these are squares, so however much I cut off of one dimension, I cut off of the other dimension. And since I'm cutting the same squares off of each side, otherwise it wouldn't make a rectangular box, then I've got xx coming off of each side, right? So the height is going to equal x. The length is going to equal 17 minus 2x, because it's 17, and then I pull off x here, and I pull off x here. And the width will equal 11 minus 2x. So what's the volume? Well, it's the product of all three of these. So it's x times 17 minus 2x times 11 minus 2x. All right. Now, if I multiply all these together, I'll get a polynomial, but this is a fine answer as far as I'm concerned right here. This is good enough. So this is what we're talking about, is answering questions like this and dealing with quantities like this. All right. So now let's describe some of the things that can happen in a polynomial. So if the leading coefficient of a polynomial is positive, it will eventually, I'm putting this in quotes, head toward plus infinity. If it's negative, minus infinity. Now, the leading coefficient of a polynomial cannot be 0 because we've decided that a sub n, the highest degree term there, has to be non-zero. So this thing does whatever, and if the leading coefficient's positive, it goes up, and if the leading coefficient's negative, it goes down. That's the basic idea. Now, if the degree is even, the left behavior matches the right behavior, and if the degree is odd, they have opposite behaviors. And what does this mean? So if I have something with even degree, then so if the degree is even, then I'm going to have either, if it's positive, it's up and up. If it's negative, it's down and down. If the degree is odd, then it'll either go down to up or up to down, eventually with, fuzzy stuff happening, squiggles, who knows, whatever, in the middle. That's basically what this is saying. Now, the degree being even or odd doesn't necessarily imply that the function is even or odd. If the degree is even, the function could be even. But just because the degree is even doesn't make the function even. If the function is even, I guess that might make the degree even. I don't want to comment on this too much because we have things that might not be polynomials, but I don't want to talk too much on that. But for sure, this implication doesn't necessarily hold. So just note that. All right, so let's do a couple of quick examples. Describe the behavior as f of x goes. Describe the behavior of f of x. Let's just fix this. Describe the behavior of f of x as x goes to plus infinity or minus infinity. Okay, we've got f of x here being negative 9 x to the 7th plus 3 x to the 6th minus 71.8. What's going to happen? Well, the leading coefficient is negative. Which implies that this thing doing whatever eventually goes down. And the degree is odd, implying that the initial and the final disagree. So it's going to do who knows what in the middle, but it's going to start out up and it's going to finish up down. All right? Now, let's see. Let's do something a little different. We could do this all day and keep doing examples like that, but basically, if it starts with a minus sign, it goes down. If it starts with a plus sign, it goes up, like I said. And if this highest power is odd, the start and finish disagree. If the highest power was even, the start and finish would agree. Let's do this one. Find where f of x, which equals, and so this would be the final answer, by the way. That's the behavior that I'm looking for the previous one. So for this question now, find where f of x equals 3, x minus 2 quantity squared times x plus 1 is greater than, less than, or equal to 0. So solution, we're going to start with f of x, which is 3 x minus 2 quantity squared times x plus 1, and we're going to set it equal to 0. Okay? So now the zero product property tells us that this thing equals 0 when x equals 2 or when x equals negative 1. So now we can do the test points thing like we did before. So let's draw a real number line out. We've got 0 here, we've got 2, and we've got negative 1. And it's going to be 0 here and 0 here. So now let's pick test points outside of these ranges. So we've got 0 in between negative 1 and positive 2, but now let's say negative 2 and positive 3. And we'll plug these into f. So let's check f of negative 2, and that's going to be 3 times negative 2 minus 2 squared times negative 2 plus 1. And I don't need to evaluate this. I just need to say whether it's positive or negative. Well, anything squared is going to be positive. I've got 3 times a positive times a negative. So this is going to be negative. So it's negative here. And let's check f of 0. So this is 3 times 0 minus 2 quantity squared times 0 plus 1. Well, this is 3 times, it's something squared, so it's always going to be at least non-negative. And then times a positive, which is positive, which means it's going to be positive here. And finally, let's check f of 3. And 3 isn't special. I could check f of 3,000, just anything bigger than 2. And this is going to be 3 times 3 minus 2 quantity squared times 3 plus 1, which is 3 times a positive times a positive. All right. So this is greater than 0, so it's positive here too. Okay, well, what do we notice? Well, this had a 0 raised to the first power. You know, there's a little invisible 1 here. And this had a 0 raised to the second power. The sign changed when we went past this 0, and the sign did not change when we went past this 0. Well, I mean, I guess the sign changed from positive to 0 and back to positive again. All right, well, there's a general phenomenon that we can describe by saying the multiplicity of a 0 is the exponent of the factor of that 0. So in this case, the exponent of the 0 x minus 2 was 2. So x minus 2 is a 0 of multiplicity 2. The exponent of x plus 1 was 1. So the multiplicity of the 0, negative 1, was 1. Okay? All right, so now let's figure this out with, let's just do an example of this with what are the zeros and multiplicities of f of x, which is 2 times x plus 2 to the 7th times x minus 19 to the 44. Okay? Hopefully you're noticing by now that when I give you some of these sort of sillier numbers, you're probably not actually going to have to use them. So at least not use them to their full capacity. So when you see this polynomial, well, it's factored polynomial, but when you see this, I'm probably not going to ask you to raise 19 to the 44th power and compute that. We're going to use 19 and 44, but not by actually foiling this out with 44 factors, right? So the solution, I'm just going to write, f of x equals 2. I'm leaving plenty of space here. X plus 2 to the 7th, x minus 19 to the 44th. So this is 0 at x equals negative 2, and its multiplicity is 7. And this is x equals 19, and its multiplicity is 44. And that's the final answer. That's all I needed. Okay, so if that was a little too quick, let me go a little bit more slowly. So again, we have the ZPP, the zero product property, or ZFT, zero factor theorem. What's happening here? Well, this is a product of three things: 2 times x plus 2 to the 7th times x minus 19 to the 44th. And if they're equal to 0, why do we care about equal to 0? Because I asked for the zeros. If they're equal to 0, if this product is equal to 0, then at least one of these component factors has to be equal to 0. Well, 2 cannot equal 0. So that's out of our, we're not concerned about that. X plus 2 could be 0, and x minus 19 could be 0. So we check these out. What makes x plus 2 0? Well, x equals 2 makes x plus 2 0. And what's the multiplicity? That's the exponent of that factor, which is 7. X minus 19 could be 0. What makes x minus 19 0? It's when x equals 19. And what's the exponent of that binomial, of that factor, is 44, so its multiplicity is 44. Now, what we'll eventually notice is that if the multiplicity of a 0 is odd, then the graph will cross the x-axis there. If the multiplicity of a 0 is even, then the graph will kiss, or just touch the x-axis there. So, you know, as an example, let's just sketch a graph of this function. Two times x plus 2 to the 7th, x minus 19 to the 44. I don't know exactly what it's going to look like, but I know that, just for fun, the leading term is going to be positive because we start out with a positive number here, so it's eventually going to go off towards plus infinity. The overall degree of this polynomial is going to be 7 plus 44. If I were to, you know, FOIL everything out, the highest power of x is going to be 7 plus 44, which is, well, gosh, I don't know. I guess I could figure it out. It's 51, but you know, it doesn't matter. It just matters that it's odd. So we're going to end up going down, you know, or coming up from the left, or going down as we go off to the left, however you want to think of it. And we've got a 0 here at -2, and we've got a 0 here at 19. So now the question is, what happens in between times? Well, I don't know the exact shapes that we're going to get, but I know that x plus 2 is a 0 with an odd multiplicity, meaning that this thing's going to do whatever it does and then go through the x-axis there. Then whatever happens, who knows? And then at when x equals 19, we touch the x-axis again, but we kiss. We just touch and bounce back up because this is an even degree.